A processor can read from or write to memory using basic load and store instructions. The load instruction moves data from main memory into one of the processor's registers, while the store instruction moves data from a register back to main memory. In the assembly language, memory operations are performed using the move instruction, which serves both load and store purposes. Here's an example of incrementing a value by 1. The first move instruction loads the value from main memory at address 1000 into the EAX register. The add instruction adds 1 to that number, and the second move instruction stores the updated value back into main memory at the same address. But this creates a bit of a problem. How does the processor differentiate between addresses referring to main memory and those belonging to other hardware components, such as a GPU's internal memory? What if the instruction was actually intended to increment a value in the GPU's memory instead? This issue stems from the fact that multiple devices can have memory regions that share the same addresses. There are two main solutions to this problem. One approach is to explicitly specify the target device in the instruction, a technique known as port-mapped I/O. The other approach is to map all devices' memory into a unified address space, which ensures that addresses do not overlap. This technique is called memory-mapped I/O. Peripheral devices connect to a system via ports, with many devices occupying multiple ports. A port is not the physical connection of the device to the hardware, but rather a logical connection point. Every connected device can be accessed by referencing one of its assigned ports. For example, on older PCs, DMA controllers were commonly mapped to ports 0 to F, while hard disk controllers used ports 320 to 32F. Historically, PCs primarily used port-mapped I/O for communication between the CPU and peripheral devices. A processor that needed to communicate with a device would execute an I/O instruction which selected a specific device and port, then read from or write to the selected port. But port-mapped I/O had a major limitation. It used a separate address space from main memory, which required the use of special I/O instructions and a separate bus to transfer data. These instructions typically transferred only a single byte at a time, which made large data transfers inefficient because they required issuing an enormous number of commands. For example, transferring audio data to the audio controller 1 byte at a time while issuing millions of I/O commands might not be the most efficient operation. This major drawback of port-mapped I/O, along with a few other smaller ones, eventually led the industry to move away from port-mapped I/O and adopt a faster and more flexible approach, memory-mapped I/O. In a system that uses memory-mapped I/O, each device is assigned a unique address range, effectively combining all system memory and peripherals into a single address space. By mapping all devices into the same address space as main memory, I/O operations can be performed just like regular memory accesses. This means the same instructions can be used, no additional bus or special I/O hardware is needed, and devices can take advantage of burst transfers and other optimizations. A typical memory-mapped device has 4 memory regions that act as its way of communicating with the rest of the system. The data input region is where data gets sent to the device from an external source. The data output memory area is where the device sends data out to main memory or other components. For example, an audio device might receive audio data from main memory, process it, and then send it to the speakers so you can hear the sound. Control registers let the processor configure or control the device. Coming back to the audio example, writing the value 1 to a certain memory address might tell the device to start processing the audio data in the input buffer and play it through the speakers. Status registers show what's currently happening with the device. For instance, many devices have a busy bit, which is a flag that tells the processor whether the device is ready for more commands. An SSD is a good example. A processor might periodically check this bit to see if the SSD is still busy transferring data, or wait for an interrupt from the storage device when the bit changes. If the bit is 1, the SSD is still busy transferring data, but if it's 0, that means the SSD is free and ready for the next task. Now let's talk about how a device's memory is actually mapped. To understand how memory mapping works, it's important to first understand device drivers, since they play a big role in the process. A device driver is a software module that allows the operating system to communicate with hardware components without knowing their internal structure and registers. This allows the operating system to support a variety of components without needing separate versions for different device combinations. The driver provides a clear interface that the operating system and other programs can use to access a shared peripheral device. When the system boots up, the BIOS or UEFI detects all connected hardware components, including main memory and any internal memory in peripheral devices. It then assigns a unique address range to each hardware component and stores this information in a global data structure called the system memory map. When a device driver starts, one of its responsibilities is to map the physical memory of the I/O device into the operating system's virtual memory space by reading the memory map. This lets the operating system and drivers access and control the hardware they are responsible for. User programs run in user mode, so they aren't allowed to directly access memory mapped devices. Instead, a program that wants to use a device, such as playing audio through the speakers, sends a request to the operating system, providing the audio data along with additional playback settings. The operating system processes the request and forwards it to the relevant device driver, which in this case is the audio controller's device driver. The driver then sends the audio data to the hardware through the mapped memory addresses and instructs it to start playback. Thanks for watching. Be sure to like and subscribe if you want to see more videos like this one. I'll see you soon.